All right, you guys, today we're looking at a big, a very enormous Algebra 1 topic, looking at how to graph all of these different parent functions. We do a lot of transformations in our algebra and in our Algebra 2 courses. So today we're going to take some time to revisit some of these parent functions. So when we call something a parent function, we're looking at it at its most raw, basic format before it undergoes any sort of transformation, whether we move it left, right, up, down, whether we stretch it or compress it, or reflect it in any way. So let me get in a little bit tighter. These are the big six that we'd like you to have down, to have locked into memory before entering Algebra 2. All right, so I'm also saying include any asymptotes. And an asymptote is a boundary line that we approach, but we do not cross it. All right, so the first one we see y equals x to the second power. We should recognize this as a quadratic function. And we should know that the shape of it is this beautiful U shape just like so. So this is a quadratic function. When we graph it, we usually use some inputs and outputs. So we plug in some values for x between -2 and +2. So picture plugging in each of these inputs into this function. Imagine that when we plug it in, they're going into parentheses. So -2 in parentheses squared becomes 4. -1 plugged into parentheses and squared becomes 1. 0 is 0. 1 squared is 1. 2 squared is 4. So if I'm graphing my quadratic parent function, my vertex right here is at the origin. So I'm just starting right there. And from here, I'm really going over 1 in both directions and up 1. So from the vertex right here, I'm going over both directions and up 1. Those are the 2 points here and here. And then here, go back to the origin. That's where we dropped our anchor. And here we're going over 2 and up 4. So I have a point here and here. Okay, and then I can connect my dots. And this is my quadratic parent function. We graph it using all of the perfect squares. So we start at the origin, and then as we go over 1, we go up 1 squared, which is 1. As we go over 2, we go up 2 squared, which is 4. If we went over 3, we'd be going up 3 squared, which is 9, right? So you see the pattern on how we are plotting our points. Okay, next function that we'd like you to have down is absolute value. So here I just used function notation. This really reads as the same thing as y equals absolute value of x. Those notations are interchangeable. Okay, so f of x is really the same as y equals. So in words, we say that this is an absolute value function. And we should know roughly that it graphs as a V shape, just like so. Okay, so we do the same thing. We make a table of inputs and outputs. So x and y. And I'm going to use the same inputs. I'm going to input a -2, -1, 0, 1, and 2. So if I put any number into absolute value bars, it just forces that number to be positive. So -2 becomes 2, -1 becomes 1, 0 stays 0, 1 stays 1, and 2 stays 2. So when I plot these points, I start at the origin. That's where I drop my anchor right there. And as I go over 1, I'm going up 1, back to my origin, back to where I dropped anchor. And as I go over 2, I'm going up 2. Okay, if I did more points, if I went over 3, I'd be going up 3, over 4, up 4, and so forth. So what ends up happening with the absolute value function is that it's like we have two lines that come together at the origin. It's just that one of those lines has a slope of +1 and the other has a slope of -1. And there's our absolute value function. Looks like a beautiful V shape. All right, next up, 3. So here I've marked it as g of x, but again, that's the same as if I said y equals the square root of x. So this is a square root function, one of many radical functions, just depends on what the index is. Our index here is 2. It's a square root. And then here is the rough shape of it, just like so. So it's good to be able to look at an equation that's given, see what kind of function it is, and have a rough picture in your mind of what it will look like. All right, so now here, inputs and outputs. So I'm going to input all of the perfect squares so I can plot nice, clean integer values. So I'll plug in a 0, a 1, a 4, and a 9. Again, those are all perfect squares. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Okay, so drop your anchor at the origin. And then from here, we're going to go over 1 and up 1, back to the origin. Over 4 and up 2, back to the origin. Over 9 and up 3. Connect your dots, and we have a square root function. Okay, next one. So here in 4, we have y equals 2 raised to the x power. So whenever we have a variable in the exponent position, we call this an exponential function. Now, exponential functions can have different base values. I'm using a base value of 2. Your base value could be 3, it could be 4, it could be 10, right? It could be anything. Okay, when I'm using anything that's more than 1, I'm looking at a growth example. Okay, if I had something that was more than 0 but less than 1, I would be looking at a decay example. I'm going to start you off with a really basic growth example. Okay, when I picture what happens when I look at an exponential function that is growing, I have an asymptote right here, this horizontal line. Again, it's a boundary line that we may approach, but we do not cross it. And what happens is our function, it keeps doubling, 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 then it starts to spike and grow really rapidly, right? Whenever we say exponential growth, we're trying to say it grows really fast over a period of time. So here, right, this would be an example of an exponential function where it's a growth example. Okay, if I use inputs and outputs, again, we make a little chart to the side. And let's say that I plug in -2 to +2. So here I'm saying, well, what's 2 to the -2nd power? Let me just write that here to picture it. So 2 to the -2nd power is like saying 1 over 2 to the +2nd power. So 2 to the -2nd power is 1 over 2 to the +2nd power. So we have 1 over 2 squared, which is 1 over 4, 1/4. Okay, and then 2 to the -1st power would be like saying 1 over 2 to the 1st power, right? It's a positive first power, so 1/2. 2 to the 0 would be 1. 2 to the 1st would be 2. And 2 to the 2nd would be 4. So look at all those outputs. Look what's happening. You can see that it's doubling from stage to stage, right? The next would be 8, and then 16, and then 32, and so forth, right? And that's because of that base of 2. If this was a base of 3, it would be tripling from stage to stage. If it was 4, it would be quadrupling from stage to stage. So let's plot those points. So negative 2, 1/4 is about right here. Negative 1, 1/2, 0, 1, 1, 2, 2, 4. If I had kept going, I would have 3, 8 as my next one, just like so. Now remember, I told you initially there's an asymptote. There's an asymptote right here at y equals 0. A horizontal line right here at y equals 0. Why is that an asymptote? Well, let's think about that for a moment. Let's say that I plugged in a negative 10 for x. That would be like saying 1 over 2 to the 10th. So 1 is being divided by a bigger number, right? It's going to be closer to 0, but not 0. It will still be a positive number, just a tiny number. So I'm hugging the asymptote, right? As I move to the left, I get really, really close to y equals 0, but I never get there exactly. So that's why we say we have an asymptote there, because we approach it, but we do not touch it, and we certainly do not cross it. So we draw it in just like so. There's an asymptote there. Usually draw that as a dotted line, like a boundary line that we do not cross, right? For whatever value of x, something that's in negative territory, it will give us a number that is very small, but it's still going to be more than 0. All right, 2 more. So here in 5, we have x to the 3rd power. This is a cubic function. Okay, and a cubic function, right, it's the same as if I wrote y equals x to the 3rd power. I know it kind of looks like this kind of sideways S, kind of like that. That's the shape of it. So I have to have that locked into my memory, right? It just helps keep me anchored in the skill. What does it look like? What does it roughly look like? Okay, and then over to the side, I'm going to make my table. Okay, and I'll use inputs and outputs again. I'll use negative 2 to positive 2. So negative 2 to the 3rd power. So picture it goes in parentheses. So negative 2 times negative 2 times negative 2 would get me negative 8. Negative 1 in parentheses to the 3rd power. Negative 1 times negative 1 times negative 1. Well, still negative 1. 0 to the 3rd is, well, still 0. 1 to the 3rd would be 1, and 2 to the 3rd would be 8. So if I plot these points, I have negative 2, negative 8 right there. Negative 1 right here. Here's my origin. 1, 1, and 2, 8, just like so. Connect the dots, and here is my parent cubic function. Again, it's kind of like a sideways S. All right, last one, very last one. Here, g of x, right? G of x, I could have just written that as y equals, it would be the same thing. It's just using function notation when we write g of x. Okay, so this one is a rational function. Sometimes we call it a reciprocal function, and I'll tell you more about that in just a minute. So here we're going to have 2 asymptotes. We're going to have a vertical and a horizontal asymptote here and here. And we have 2 branches. We're going to have a branch up here and a branch down here. Okay, so again, I'm just locking this into memory. I'm trying to think, okay, when I see that function, what does it look like roughly? Okay, so now table. X, Y, inputs and outputs. I'm going to get a few extra ones here. I'll go negative 3 to positive 3. All right, so if I plug in a negative 3, right here I have, well, I have negative 1/3, and then negative 1/2. 1 over negative 1 is, well, negative 1. 1 over 0 is undefined. And that's why we're going to have an asymptote right there. So I'll talk about that again in just a moment. 1 over 1 is 1, and then 1/2, and then 1/3. Okay, so I'm going to first put in my asymptotes. So I have an asymptote here. X cannot be 0. So I'm going to draw in this vertical line here at that vertical asymptote where x equals 0. So why is that an asymptote? Well, that's an asymptote because if x was 0, this would be undefined. I have another asymptote that's horizontal at y equals 0. We draw that in as well. So again, dotted line, a boundary line that we could approach, but we do not cross. So why do we have one here at y equals 0? Well, could y ever be 0? What would x be that would create y equal to 0? Well, that's impossible because I have a 1 in the numerator position, right? There's no way to get a y value of 0 if I have 1 in that numerator position. I would need to have a 0 there to get 0 overall. So it is an impossibility. So I have these two asymptotes. So now when I graph these, I usually just picture these points down below, and I'll show you why in just a moment. Okay, and then it makes it easier to get these ones right here. So my first point is 1, 1. So right here, 1, 1. Okay, my next point is 2, 1/2. So as I go over 2, I go up 1 over 2, right there. And as I go over 3, I go up 1 over 3, puts me right here. Now remember how I said that this was a reciprocal function? Well, if I had 1 and I divided it by 1/2, it would give me 2. So this point that was 2, 1/2, I could have 1/2, 2, and 1/3, 3 as well, and it just helps me smooth out my curve like that. So I have my first branch in place. So now I need my other branch down in this quadrant. So I start with the over 1 down 1, like that, and then as I go over 2, I go down 1 over 2, so right here. And as I go over 3, I go down 1 over 3, so right here. Okay, and if I want those reciprocal points, here over 1/2 and down 2, over 1/3 and down 3. Right, it just helps me smooth out my curve even better. So there we go. There is my rational function, right? 1 over x, y equals 1 over x. I have those two asymptotes, and an asymptote is a boundary line that we approach, but we do not touch it. We certainly do not cross it. All right, that is all I have for today. Have a good rest of your day, guys.